Chingaté. I'm from Colombia. My work is titled In Silico Design of Analogous Peptides Derived of Bombina Space with Improved Antimycobacterial Activity in vitro. The focus of our research group is to find possible ways to controlling the spread of tuberculosis. The TB is possibly the most prevalent infectious disease in the world. The WHO estimates that 1/3 of the world population is affected. Annually, there are over 8 million of new cases of TB and cause 2 million deaths per year, which are alarming numbers. So, if we have vaccine and we have drugs available to treat TB, what is the problem with this disease? So, we need to find new compounds for the treatment against tuberculosis. Some problems with TB control is co-infection with HIV, low efficacy of BCG vaccine, fault accessibility, rapid diagnostic methods, and emergence of resistant strains of tuberculosis against anti-TB drugs. So, in this panorama, we want to speak about antimicrobial peptides, yes, because they are very interesting molecules because have some important response. First, they are part of innate immune response. They are synthesis in tissues exposed to microbial attack and inhibit or retard the growth and help to analyze in mechanisms of natural and adaptive immunity. So they have some interesting activities: antibacterial, antifungal, anti-tumor, anti-cancer, etc. This kind of molecules have very interesting mechanisms. Yes, as said before speaker, has several mechanisms, all as theories, but the initial start by electrostatic electrostatic interaction with the membrane. You know, the membrane have phospholipids, so have high electronegative share. So with the interaction electrostatic going to start, they open the membrane. So have some important structure points: length, sequence, share, secondary structure, amphipaticity, and hydrophobicity. Our experimental strategy was first step bioinformatic design. We use some tools for determining antibacterial activity, helical structure, amphipaticity, and positive share. The next step, synthesis and chemical characterization, and finally biological tests, minimal inhibition concentration, hemolytic activity, inhibition of basal ATPase activity, and cytotoxicity activity. In the first part, in silico design of antimicrobial peptides, first we can see the two native sequences we work, bombina and maximine 1. This is the native sequence. In orange, you can see the part with helical structure. We use for the bioinformatic designs this anti-BP server, and for the development of this server, they use antimicrobial peptide database. So this antimicrobial server permit we mapping all the primary structure and going to find the sequence with 15 length with high score antibacterial. So this is in silico bombine analysis. You can to see here the primary structure, then under a secondary structure. So the server permit to determine which part of 15 length have the high antibacterial score. It's in red. So we're going to name this the blank peptide bombine A. Then with this blank peptide, we do some change in the primary structure in red, you can to see, and try to increasing the positive charge, and this is the antibacterial score. This is the helical wheel representation, you can to see. So you see two parts important. First is the polar phase. This is in blue, that this permit the electrostatic interaction, and this non-polar phase so permit the internalization of the peptide into the membrane. Similar analysis we do with maximum 1. So this is whole native sequence, and under is the secondary structure. Of this, we determine this is the peptide with 15 length. In red, we did some change, increasing antimicrobial value and share too. We can to say to before, we say a polar phase and non-polar phase that permit the interaction with membrane. About the chemical characterization, we make the purification with high performance liquid chromatography. We can to see in all the cases just one signal, and determine the mass by Malditov. About biological tests, well, first we determine the viability of Mycobacterium smegmaticus in presence on bombine and maximine 1 modified. You can to see bombinine A, bombinine B, yeah, so this is the modified, and maximine 1A and maximine 1B. In both cases, we can to see decrease the concentration necessary for the viability, yes, of the bacteria. Hemolytic activity, you can to see the mostly case is not a surprise at 10%. Only maximum 1B have 20% of hemolytic activity, so need do another design for this peptide. Some peptides have inhibition of some enzymes, very interesting, on ATP's activity. However, our modified peptides don't show this high inhibition of some ATPase enzymes that they are essential for the cell viability and holding process crucial to cell function. That means have another target into the cell. About toxicity activity, we determine murine macrophagus, and it shows All peptide shows cytotoxicity using higher concentration compared with the results in minimal concentration inhibitory test. Finally, as conclusion, overall, it was determined that the design of a peptides doing change its primary structure to improve future like helical structure, antibacterial, and shelf value allows to develop new strategies for designing antimicrobial peptides as anti-tuberculosis compounds. Thank you very much.
Thank you, Dr. Chingaté Lopez, for giving your very timely presentation. Thank you for that. Are there any questions? It was a clear presentation as well. Really, no, yeah, question from the back.
I'm not sure I was very clear. The peptides that you synthesized or you produced, I just want to know if you were successful in optimizing antimycobacterial activity. And I also want to know if they were all acting by the same mechanism, or what was their target? Did they all have the same target, or were they all acting
Okay.
by the same?
We synthesize the peptides, but we find some reporter peptides against another bacteria, no tuberculosis. So what we do, we change, we know the rational design of peptides permit increasing antibacterial activity. So we did that. So change in the primary structure. So then when we synthesize, purify, etc., we do biological tests against the mycobacterium. Yes.
You modify the primary structure, but the ones you produce do not necessarily show high antibacterial activity.
Yes.
When you are using antimicrobial peptides, is there also a risk that you get an elevated level of LPS? Because you have the intruding peptides breaking down the membranes, and LPS could be coming into existence at that moment. And that is also negative for an infection. Could you explain a little bit about that?
Yes. Well, not necessary go against the membrane. Yes. This is one mechanism. We can to it can to break.
It disrupts the membrane.
But well, to come inside, for example, find another target like nucleic acids, for example, and don't permit the viability of cells.
Okay,
No,
thank
for
you.
the question.
It was more about the LPS molecules which are freed from the membranes. Okay. And there's one question more.
I want to ask this question for the first who was she was working on peptides too. The sequence of amino acids and the nature of amino acids to synthesize the peptides. At first, for the composition, all of your amino acids are proteinogenic, or there is another type of amino acids, because in nature, especially by bacteria and fungus, there is
use the microphone because it seems that some was missed.
Okay. So, if you want to know how doing change this increasing the electrostatic interaction, is okay?
First question, the nature of amino acids.
Uh,
Proteogenic
So
or
how to change the amino acid? Oh,
their sequence.
okay. Do you remember I show this one? Exist this antimicrobial peptide base, yes? Oh, for answer your question. So they have many, more than 2,000 antimicrobial native inside, yes? So they determine how which one of amino acid is more expressed in this primary structure of native structure. Understand? Yes. So which one? Wait. So they determine, for example, the positive charge going to interactor with C terminal. Yes. And in the C terminal going to interact with membrane interaction and N terminal with amino acid acid nucleic interaction. So and determine which one of amino acid have a high frequency in these cases. For example, lysine, yes, cysteine. So we make subchains for this kind of amino acids, and then determine the antibacterial value by anti-BP survey. And the second was which one? The another question. Excuse me, doctor.
The
Charge
second question.
positively, positive because the membrane charge negative. So you don't have answer.
Okay, sí, señor.
There was one question more, I think, in the audience. Or not? Probably it's answered in the meantime. No? Okay.
Thank you very much.
Then you have answered more questions, and I will give you the certificate of verification for this